double integrals over general regions. Find the volume of the solid bounded by the paraboloid and the plane. We're going to find out that doing this problem in cylindrical coordinates is much simpler and faster. For now, we'll be using rectangular coordinates. So how do you find the volume of a solid? Well, you break the solid up into prisms. So let's make ourselves an arbitrary prism and find the volume of that prism. Well, the volume of a prism is height times the area of the base. In our case, the height is the height of the plane minus the height of the paraboloid, and the base is just dA. Where will the bases dA come from? So what's our region over which we will integrate in the xy plane? Well, in the given solid, the plane stays above the paraboloid. And so we're looking at the region in the xy plane such that 5x squared plus 5y squared, the paraboloid, is always less than or equal to 5, the plane. And that's just the region x squared plus y squared is less than or equal to 1. And as you know, that region is a circle in the xy plane centered at the origin with a radius of 1. Now, to make the problem a little bit easier, I'm just going to look at the first quadrant. And in the first quadrant, I can describe the circle as y equals the square root of 1 minus x squared. And so my region of integration in the first quadrant will be y runs from 0 to radical 1 minus x squared, and x runs from 0 to 1. Then after I do it in the first quadrant, I just multiply my answer by 4. So I set up my integral using my volumes of my prisms and my first quadrant and multiplying by 4. Before I continue, I'm just going to pull out that 5. So let's move on to a new slide, and when we do that, let's integrate with respect to y. So we're going to do our first integration. It's with respect to y. And after we integrate, we need to evaluate. So evaluate from 0 to radical 1 minus x squared. And to simplify this, we notice that every term has radical 1 minus x squared. So we go ahead and pull out one factor of radical 1 minus x squared. And I'm going to now switch slides again, and the bottom line you'll see at the top of the slide. Okay, so there's our equation again. Notice that I have a radical 1 minus x squared. That's being squared. Well, go ahead and do that squaring, and I'm just left with 1 minus x squared. And then I combine like terms. And then I rewrite my radical so that it's in exponent notation, and that makes it a little bit easier to multiply these two things out. All I have to do is add the exponents, because the bases are the same. To do an integration like this, I really need to use a trig substitution, x equals sine theta. When you do a trig substitution, x equals sine theta, you're saying that theta runs between negative pi over 2 and positive pi over 2. So anyway, if x equals sine theta, dx equals cosine theta d theta. And then 1 minus x squared is the same as 1 minus sine squared, but 1 minus sine squared, using the Pythagorean theorem, is just cosine squared. And so if I want to know what 1 minus x squared, all of that to the 3/2 power, I'm looking at cosine squared to the 3/2 power. Now, one thing to keep in mind is that if theta is between negative pi over 2 and pi over 2, then cosine is always 0 and greater. And so this, the right-hand side simplifies very nicely into just cosine theta to the 3rd power. All right, so next we need to think about our bounds. We've discovered that 1 minus x squared to the 3 halves, that's cosine to the 3. We found out that dx is cosine theta d theta, and the 40 over 3 just gets transferred. And so what are my bounds? So if x equals 0, then let's say sine theta would have to be 0. And if theta is running between negative pi over 2 and pi over 2, then theta has to be 0. Now let's do the top bound. If x equals 1, then sine theta equals 1. And again, theta has to run between negative pi over 2 and pi over 2, and so theta has to be pi over 2. And so I go ahead and multiply. I had cosine to the third theta times cosine theta. Well, that gives me cosine to the fourth theta. All right, cosine to the fourth theta, that also is not very easy to integrate. So I don't know, take a deep breath. We still have some work to do. Cosine to the fourth theta, what we're going to have to do for that is 2 iterations of the power reducing formula, or you might know it as the double angle formula. So cosine to the fourth is cosine squared squared, and then cosine squared is just 1 plus cosine of twice the angle over 2. And then I end up with a cosine squared again, so I have to use the double angle formula again. And then deal with the fractions, and when I'm all done, I get this last line. So instead of integrating cosine to the fourth theta, I have something a little easier to integrate. Go ahead and pull that 1/8 out to simplify. We're now finally ready to integrate. So integrate with respect to theta. Integrating with respect to theta, I then evaluate, theta being 0 to theta being pi over 2. Now notice when you evaluate for theta being pi over 2, your second and third term are both going to be 0. And when you evaluate for theta being 0, all the terms are going to be 0. And so I'm going to be left with 5/3 times 3 pi over 2. And when the dust settles on the arithmetic, I get 5 pi over 2. And we are done. So 5 pi over 2 cubic units is the volume of my solid. Take care. Have a great day.